Welcome everyone back our lessons. I hope everyone is not so boring about this part. Okay, this is one of the other lesson related to the introduction to the quantum computing and the programming. I hope everyone can learn a lot about how you present, the quantum state in the Bloch sphere. And today we will look more about how the equivalent class on the Bloch sphere and how you can know the two vectors can have the same state. Yeah. So okay, we will look back about this guy the new theory. Yeah. Okay. Now we have two. Yeah. This is kind of very important when we have two vectors. We have a two vector. So how we can know two vectors have the same class, or we have two vectors is same state? So in quantum computing have one condition. If the two vectors have the same canonical state, so they can have the same equivalent class. Okay, I will make a visual the example like this. So this guy the quantum sphere, right? So we have a 3 dimension. What is canonical state? Canonical state that means you can transfer to the kind of the 2 dimension. 2 dimension. So if the two vector in the 3 dimension, and they transfer to the 2 dimension, and they have the same position. That means they can have the same state. Yeah, that is the one very important because if something we calculate in the 3 dimension is more complicated and we're not sure they have a same direction or they have a same the pole, north pole or the south pole or something like that. So we need to find a way to check if they have a kind of equivalent class. So this kind of the one of theory, we cannot do that. So over here, the one of key point, I hope you remember, if the two vectors have the same canonical state, so they can say they have an equivalent class. Yeah, that is the key point. And we will look how we can prove that kind of information and how we can the transfer or the associate the value. Okay, similar like this. If we have one constant value, yeah, or we have one vector. So one vector and the constant. So actually, this one remind you the one vector can be have the same the canonical state with itself. Okay, if you see the x and can have a same state, same canonical state with itself. This one is very important to maintain the integrity for the one quantum state. Yeah, to make sure you cannot transform by yourself. And if you want to transform by yourself, yeah, so that means the zero version, yeah, so it will be transformed too. So we have the other part is symmetry. Yeah. So actually that's kind of very important. If x and y, the quantum vector x and quantum vector y have the same the canonical, and this kind of reverse way, if the quantum vector y and quantum vector x have the same canonical, yeah, it's similar. We have this way and we have this way. If the two one is kind of similar, same the canonical state, so we can write in this part, yeah. This part and this part have the same meaning. Okay, have the same meaning, and to make sure they can have the same, the equivalent class. Yeah, equivalent class. And the next one, this one is kind of how we transfer to the, x and y, and from the y and z. So that means we have x and z. Yeah. Okay. Yeah. So this is kind of transitive. Yeah, transitive. X and the Y, the quantum X and quantum Y have the same mechanical state, and quantum Y and quantum Z have the same mechanical state. So we cannot say quantum vector V and the quantum vector Z have the same mechanical state. So this kind of the definition. Yeah. So we cannot say that's one. So and over here we have alpha. Yeah, alpha. So alpha is kind of equivalent relation. So to make sure we can connection between these two, to the vector. Okay. So and the next one we have the beside we have a transitive. We can have we have the part we have a quantum transfer between the quantum state in the complex vector. And if the two vector u and v have a same mechanical state, so we would say the u vector quantum u and vector quantum v will have a same corresponding point. Same corresponding point in the Bloch sphere. Yeah, Bloch sphere. That's something like this one. Yeah, in the Bloch, this kind of Bloch sphere, if the vector u and vector v have the same canonical state, that means we can have the same. Yeah, maybe we can have same over here, or we can have the same this part or same this part. Yeah, so that's kind of to make sure if the when the two state can have a same state in the the quantum. So to make sure, yeah. So the condition that guy they have a same mechanical state. That was same the position in the 2 dimension. Yeah, 2 dimension. Okay, the other is how to prove this one. So we can use this guy. Remember, we have this guy the Euler, and we have a Hopf map, right? We have Hopf. This guy we have a Hopf map. So based on this one is C. Yes, this one is C. C over 2. So after we transform over this one, we can transfer to the this is one is real number is over 3. So, but this one you cannot say the values in the quantum state. We only rely on the 2 value. Yeah, 2 value. The theta and the phi. Okay. And okay, now we can look more detail. So when we have the quantum, the quantum. The state u and quantum state v. If we use a kind of the Euler formula, this Euler formula, and Euler formula, and this is kind of you transfer to the complex vector. Okay, complex vector. Yeah, after you can and you transfer and this one and you can match. Yeah, match this one. Remember the last time we transfer this one and to multiply, and this one is from the previous one in the Hopf map. Yeah, Hopf map. Yeah, you can this kind of value actually over here you can transfer to the cos phi 0 and cos theta over 2. You can move to outside. Yeah. So similar to this one for vector, vector u quantum, yeah, and this for vector quantum v. This is v, okay, v. Yes, v for v. And after we calculate, so use a Hopf. This is remember this is a Hopf, yeah. Okay, this one Hopf from Hopf map. So after we use this one and we can use Hopf, this Hopf. Remember we have a Hopf map. Okay, calculate a Hopf map. Yeah, calculate some Hopf map x equal to 2. So based on this value and you calculate. Okay, so this guy of 2 value have this one is the same, right? This same, right? This same, right? And this same. So we move this one from the outside, yeah, from the outside, yeah. And after you calculate, you can see and replace this kind of value to this one. So you can have the final one have this one, and after you minus this one for this one, so you only have this one, right? Yeah. Okay. This is how we can exploit some, the Hopf map and to calculate about x value in the, x value or y the value in the, y. This is y, and the z, we have a z. So this one is how we use it, the Hopf map and to transfer and to calculate the value in the Bloch sphere. I think that this kind of we already learned about it in the previous lesson. Yeah. So over here the key point. After we have we have a three the vector this one in the 3 dimension, and we transfer to the the quantum vector, and they only depend on the theta and about the phi, the two value. Yeah, this and to the value, and the polar form can represent. Yeah, you can see. Yeah, actually this one from the previous lesson we already learned about that. Yeah, so I want to skip quickly over here. So yes, this one is final thing. We can see if the two vector u and vector v have the same canonical state. That means you can see the corresponding point between the 3 dimension and 2 dimension. For example, if vector v and vector u have the same position, over here, so you will see we'll have same popping point over here, right? It's similar like when we have two position, but if we see in the Bloch value in the 2 dimension and it's the same position, so we can say okay, in the 3 dimension it will have the same position too. Yeah, that's one of very critical information in the quantum. Okay, because quantum working on the 3 dimension, but when we calculate and computing, we need to move to the 2 dimension. Yeah. Okay. So over here we have a key point. Yes, we have a key point. We need to remember how we use a Hopf map. Yeah, Hopf map to transform to the quantum vector. Yeah, to quantum vector. And the second, the quantum vector u and the quantum vector v have same canonical state. Same canonical state, so they can say if they have a same canonical state, we can say they have the same quantum state and in the Bloch sphere. Yeah, so that's the key point. I hope everyone remember. Thank you, everyone.